So hello, my name is Sammy. I'm an undergrad here at Columbia, and my project was on trying to capture atmospheric profiles using variational encoder-decoder networks. So I'm not going to go too much into the background because it's very similar to what has been presented, but essentially the motivating question for my research was, we have this regression task of very high dimensionality, where we're trying to resolve the macroscopic influences of convection. And I was animated by, can we use the power kind of a data-driven deep learning approach to have a fast solution to this regression problem, but also retain insight into how our regression is generated and how the model is performing? And can our model help us understand convection itself better? And so those were kind of my goals in outsourcing this to machine learning. And so to do that, I focused specifically on as I said, VAE networks. And so in case you're unfamiliar, the goal of VAEs is basically to force an information bottleneck by having a layer in the middle that is very small. And this essentially approximates nonlinear principal component analysis. And so we're trying to capture the variance in our data by compressing it into this kind of bottleneck and then decoding it solely from that limited information. And then one other noteworthy thing about VAEs is it encodes inputs as distributions. And so instead of just learning vectors, we interpret those vectors as the means and standard deviations of Gaussian variables. And so when we sample from this lower dimensional representation, which is referred to as a latent space, it kind of gives us this degree of control over our generative model. And so if we're talking about extremity, if the model does its job well, we can sample how extreme we want our generations to be by controlling that learned sigma parameter. And so VAs are a really promising way to try to understand macroscopic drivers of convective processes, because by trying to interpret what the dimensions of the latent space correspond to, we try to understand what is most significant for the model in the decoding process. And so the encoder and decoder are trained jointly on a combination of regularization, of trying to get smooth properties that I'll talk about later, and actual accuracy of the task. So for my data set, I was focusing on these inputs and output variables. And so there are 44 dimensions to the input vectors and 43 for the output. Perhaps if I continue the project, I would try to capture the full range of variables. And I took daily averages. So this is more specifically the architecture that I focused on throughout my work. One thing to note is in this VED network, or variational encoder-decoder, we are not simply just trying to reproduce the data, as would be the case in normal VEs, but simultaneously trying to solve the regression task. So essentially, we're hoping that a model does two things at once. First, it tries to map the input itself and kind of reproduce it from the bottleneck. And second, it tries to solve the actual regression task by having these y-hat vectors. And so although this might make it harder for the model, the hope is that that makes the latent space learn more important features, because it has to capture semantically important information for both the input space and the output space. And so that's really the goal of doing this. I also benchmarked the model because I couldn't use the ClimSim benchmarks because of differences in methodology and data processing. And so I just trained really quickly a linear network and a vanilla artificial neural network, each with 32 hidden layers and 1 to 2 layers, depending on the two networks. It was trained with the Atom optimizer. The second thing I want to mention that's going to be kind of a theme throughout the presentation is this trade-off between accuracy in terms of mean squared error and KL divergence, which tells us how different the distributions we've learned are from our prior distribution on how we expect our distribution to be shaped. And so this is kind of a regularization term that tries to enforce properties within the latent space so that when we generate, things are smooth and sensible. And these are in conflict. So the more you try to make the latent space regular, the harder it is to actually get the regression task. And that's turned out to be really important when I was comparing different models. So for my analysis, I focused on one specific one to keep things consistent, but I actually had very different results depending on different choices in architecture. So this is just really quickly to highlight that point, where what I did for the model that we're focusing on is anneal this beta parameter from a very low value to a higher value. And so initially, I'm just telling the model to reconstruct the data. And as more time passes, I'm trying to make it care more and more about regularization. And so as you can see, this KL divergence starts to initially go up, but then really goes down. But as it gets lower, we start to see our reconstruction loss actually start to creep up. So these are my empirical results. As you can see, the encoder network, as expected, did perform slightly worse than the standard neural networks because of the influence of that information bottleneck, but not significantly worse. And so we have this trade-off where we are going to perform a little bit worse on our regression, but with the benefit of kind of the things that we're going to talk about in the next slides. Two things of note that I want to point out. First is I tried seeing how affecting the dimensionality of the latent space affected the test loss. And one would expect that as we have less and less of a bottleneck, the loss goes down. So something like this, but it seems to not really matter. And that's going to be important and was actually initially very puzzling, but then made sense when we looked at the actual results. So this is the result of plotting the latent space. And so what you're seeing is we're learning 6-dimensional representations, and we're doing principal component analysis on those 6 dimensions to find the 2-dimensional subspace of maximum variance so that we can actually plot it and look at things. And what you see is this very strange behavior of kind of being like linearly divided. And so this was one with a much more regularized thing. So this is kind of like what it should look like. And the 2 things we want are structure, as like we see here, and separation of important information, which we actually see in both. And so these are how output variables might be distributed differently, so that when we sample from the space, we can decode different kinds of representations. Yes. And so now this is a more detailed analysis of that. And so we are perturbing this first dimension of the latent space, which was kind of the most regularized, and traversing along it to kind of see if we look at one specific dimension, what does that correspond to? And so what we actually see is the principal components of the latent space are basically the same as just the 0th dimension, which helps us explain our bottleneck. So basically, we're giving our model 6 dimensions to learn from, but it's really only using the first one, which is a problem, but which is why the dimension didn't matter. But what we do see is this dimension is really well decoded into meaningful information. And so we see that as we traverse the latent space this way, the precipitation values follow almost linearly. And that kind of indicates that this dimension is really capturing variation precipitation. So our model has learned that I'm going to, instead of 44 vectors, learn 6. And the first one corresponds very strongly to the precipitation profile, with the temperature profile still having structure, but not being as separated because of this symmetry. Now, the last thing I did, which is more of a proof of concept, was initially I wanted to do causal representation learning to try to learn embeddings that were not just good at decoding, but were actually causally important for the for any given label of interest. And so the key quantity of interest here is this metric called the probability of sufficiency, which is basically really simple, where if we treat our variables as light switches, if we turn on a certain embedding value, how does that intervention change the value of our output? And so it's if we force maybe this first dimension to adopt a specific value, does the precipitation change, which would capture its causal value. So Amanda was talking about kind of those assumptions of causal sufficiency. And because I was uncertain whether those held for our encoder-decoder network, I actually tried this ad hoc method of approximating this, where I discretize the variables using the bins. And so this is the distribution of the variable. And I just treated it as taking one of 3 continuous values by seeing which interval it fell in. And by forcing it to take a value, I would make it jump from one or the other. And then the value I would make it take was just uniformly sampled from that interval. And so that's how I approximated interventions. And instead of trying to estimate counterfactual quantities, which I was really uncertain about the accuracy of, I just used k-nearest neighbor search to find the actual data point that was the most similar to this forced value. And from the index of that data point, I looked at the ground truth y variable. And so this was basically to sidestep in a lot of the literature kind of the complexity of trying to do direct causal analysis, but that would be a really interesting next step to try to get to. And so The results that I did when I ran this were actually on a separate model than what I've been showing you. So I don't have the table for that, but it would be in the appendix. And so, yes, I think what this has noticed is that there is some success for the encoder network to capture things that when we decode or interpret, like do give us insight into the process. We see how convection, temperature, and precipitation were kind of distributed with depending on your preference, like acceptable decline in regression performance. But for my next steps, I would definitely try to balance this trade-off better. So try to get a comparable regression performance, but have a similar regularization. So the latent space isn't basically just a line, but is more of a multi-dimensional distribution. And I'll try to make these more disentangled. So it's kind of not just relying on one number. And then there's a lot of tuning I want to do. But then the other thing that I'd be really excited to do is to actually try to extend this beyond this and estimate these causal quantities without relying on like the existing data points and trying to estimate the underlying distribution. So yeah, thank you so much. I want to really thank the RU mentors because I think they really helped me learn a lot and it was an incredibly valuable experience. And so I'm really glad I got to learn so much this summer. And yeah, does anyone have any questions?
Yeah, I have a question for your latent traversal. So you were able to, I just wonder, do you know like the first PC is most related to which input variables? Do you have an idea of that?
Yeah. So that's a great question. To better explain what these red dots are, I took the average vector of the latent space and I was perturbing solely the first dimension of the 6. And so like kind of traversing this distribution. So to your question about which variables they're the most related to, I actually did not compute this plot for all of the 43. So I focused mainly just on precipitation and temperature due to time constraint. So I can at least see that it seems to be focusing more on precipitation than temperature, because I guess it's more, like given this, you can decode this more easily. It's more of a bijective map. But I did not look at like all 43 inputs to see, or outputs to see which one is most correlated to. But it seems very well correlated with temperature. Burke.
Hi. So my question, well, a couple of parts, but my first part is, what are the Y labels you're trying to predict again?
Yeah, so my goal is to try to capture like convective profiles. And so ideally it would kind of be the entire outputs. But in this case, there's a 43-dimensional output of specific humidity, air temperature, heat flux of various varieties, and precipitation. And so the actual goal would be to try to capture like everything that's going on in the atmosphere within the embedding.
And so the output, I see there's some variables that are duplicated between the input and the output space.
Yeah.
Could you maybe elaborate on that?
Yes, exactly. I definitely can. And so with the grid cells, essentially what's happening is we're tracking temperature and precipitation, let's say, in each region of these columns. And what we're trying to do is figure out how does convection change those. And so essentially what you can do with these two outputs and inputs being the same is we're seeing how temperature has changed as a result of clouds. And so another way you can do it, which is essentially doing the same thing, is if you have temperature, you're trying to predict like the change in temperature or like the DT. So if it's like a dynamic system, you're trying to map from like the state to like the change in state. So this is basically like temperature and then like how did temperature change because of what the clouds were doing.
Okay, I guess my last question then is, could you elaborate on the purpose of the VED architecture instead of just a regular VAE or just a regular classification model? And also, if the linear model performed better than the VAE, does that inform anything about, I don't know, the distribution of the variables or something?
Yeah, those are both really good questions. So the VED is quite similar. The only difference is like traditionally when people talk about VAEs, they're more of an unsupervised approach that are trying to recreate data. So you have a data set of samples and you want to generate data that looks like those samples. I'm trying to ask more of the model and try to not just have this reconstruction task, but simultaneously force it to a regression task. So I guess it's basically really similar, essentially the same thing. It's just that I'm concatenating the outputs of both the input and the output to try to get it to do unsupervised and supervised learning. But in terms of the actual like implementation, it's very similar. Oh, and your last question was about the high performance of the linear model. Actually, that was an excellent question, and I was actually quite surprised at how well the linear model did compared to even like the neural network with non-linearities. Yeah, actually, I was also like puzzled by this, but I guess those baselines were created very recently, so I haven't fully thought about it.
Yeah, especially you have a high correlation, maybe plot the scatter plot of the predicted and true values of the some outputs.
Yeah.
And for your loss function, I think maybe you can add a weights for the reconstruction error and the regression error.
Yeah.
Because I feel maybe most of the loss problem comes from the reconstruction error. I don't know. But maybe try add some weights. Yeah.
Yeah. So that would also definitely be a next step of like trying to understand whether the model does different tasks like variationally well, and if it's better at predicting input variables or output variables better, but then also like, is it better at some, like, is precipitation easier than like humidity, for example? So yeah, I definitely would want to continue that analysis if I had more time.
We do have one more question really quickly. A technical question from Rohan Kulkarni. Can you expand on why KL divergence is an appropriate regularization term?
Sure, Rohan. Okay, so KL divergence, I didn't write it here, but what it represents is for two given probability distributions, how different they are. And so it's actually the expectation of the log of one divided by the other. And so essentially, underneath the hood, conceptually, this is all about like this family of like distribution estimation methods called variational inference. And in those, there's a trade-off between matching the prior and matching the data. And so in this, we assume like that our latent space is distributed with like normal Gaussian variables. Maybe Suba in a presentation can correct me whether that's a good assumption or not. But so we are saying when I encode the X, how similar is it to our prior of just a standard Gaussian that's like mean centered? And so the reason it's a good regularization parameter is enforcing it to try to be similar to a Gaussian has the properties that you want it to look like this, essentially. You want it to be a high dimensional Gaussian with the things clustered together so that if you sample from different points of the latent space, they're all meaningful. Because for example, in this model, if you try to decode a point here, it might just decode to pure gibberish, which would be bad, right? Because you kind of want the stability of the latent space. But here, kind of, it is nicer for that reason. So I guess it's for, yeah, those reasons.
Thank you, Sammy. And we have our last presenter, Soba. Thank you.